Welcome to Season 10 of the Prosthetics and Orthotics Podcast. This is where we chat with experts in the field, patients who use these devices, physical therapists, and the vendors who make it all happen. Our goal? To share stories, tips, and insights that ultimately help our patients get the best possible outcomes. Tune in and join the conversation. We are thrilled you are here and hope it is the highlight of your day.
Hi, everyone. My name is Josh Pelz, and this is another edition of the Prosthetics and Orthotics Podcast with Brent Wright. How you doing, Brent?
Hey, Joris. I'm doing well, man. I do have a question for you, though.
Okay.
All right. So AMS. I'm starting to see this more and more. It seems like you have a really great line of speakers. I saw Jenny Chen, and then his name is escaping me now on the it's the straddling of the public and private sector. But I'm excited to hear and see some of these people. But for our listeners, can you what the goal is of that? I mean, it seems like it's a very intimate group, right? And it's more the realist side, it seems, at least from the outside looking in, on what is actually going on in additive manufacturing.
Yeah, well, so for about 8 years actually, we've been organizing at the 3dprint.com. We've been organizing additive manufacturing strategies. And for 8 years, it's been an intentionally small event. Like, for example, when everybody's doing hybrid, we were like, no, it has to be, or now when post-COVID, we were like, no, it has to be, everyone has to be live, everybody has to be in the room. It's kind of intentionally kind of an event that maybe doesn't appeal to everyone. It definitely doesn't appeal to like casual people who are like, oh, I'll see what's up. And it's basically, let's say 300, 400, maybe 500 people, not more than 500 people in a room in New York. This time, 4 to 6 of February, and talking about strategies, talking about what's happening, talking like last year, we kicked off and kind of in a kind of very sad note where I was like, I opened up and I said like, okay, guys, this is going to be a very tough year. And I think a lot of people, this is really funny, a lot of people disagreed with me afterwards. I said it was like a seminal year or something, and that it was going to be a make or break year for additive. And a lot of people disagreed with me. And I think, I'm like, well, I don't know. Sometimes, I'm not one of those like really demure people who would be like, I'm not going to do that. I'm going to do that. I told you so, And then we had, last year, we had then Yoav, Prosthesis Yoav, talking about, consolidation and what needed to happen from his point of view. And we had the other Yoav, the Dimension Yoav, talking about his view on consolidating the market and all that. And if we see what happened with those initiatives and what happened to those big companies and stuff, it's really exciting. So we're trying to get really literally everyone in the room, and we try to get more. And the difference between other events, where AMUG is more like technical nitty gritty, let's take the machine apart, and Rapid and Formmax are more events of like doing sales or meeting people. This is really like, hey, let's talk about the business. You know what I mean? Let's talk about like how are people making money? Are we making money? Do we need to go into medical? If we want to go into medical, how do we go to regulatory approval? Or what are the challenges out there for like actually getting additive manufacturing hospitals? So it's much more kind of like a C-level-ish kind of thing, I guess, and a business people-ish kind of event. And that didn't exist yet. So when we started doing this like 8 years ago, and that's it. And I host it. And I help with like a whole bunch of people, like the Barnes Group helps us. Actually, Cantor Fitzgerald helps us as well. AM Ventures helps us as well. We help program this event, and there's a ton of people like at 3dprint.com. We're all on a really big team. So there've been a ton of people like Missy and John and stuff have been working on this. Basically, we start on this a month after the event. So on March, we start for the next year, February. So for a small organization like us, this is like a huge thing. It's like a big, big deal. So I don't know if it's interesting to the user. Like if people are listening to this and you're really about additive, I think it's a really great place to meet people and to meet a lot of people and have really fundamentally interesting conversations. It's probably the best event out there for that. Especially if you're doing that, if you want to have you and there's other events like I think AMUG is also a really wonderful way to meet a lot of people, have really good substantive discussions, but there's more kind of about the deep look into the technology. We're more like about, hey, the companies, what's going to happen? Who's going to buy who? What's going to happen to the specs? That kind of thing, and that's kind of what we're talking about. So really exciting for us, and again, we're a small organization. This is like a make or break event. If it doesn't like go really pear-shaped or anything, then we're fine, and we're much less stressed for the rest of the year. But now it's pretty much go time. It's about 20 days away now, and 20 days and 21 hours away, actually. And so, yeah, it's very exciting. And so I'm one of the two presenters of the event as well. And so I get to kind of introduce everyone and stuff, and that's a lot of fun. And I really love meeting people there. So it's more for, if you're like an orthotist and you want to stick to your practice, do 3D printing on the side, I think maybe you'd get more value out of going to an AOPA event or something like that, or a place where you can just meet each other. But if you're really into additive and really want to take a deep dive into it, then yeah, it could be really cool for people if they're listening.
Well, yeah, and it sounds like more the business side, right? So
yeah, totally.
The C-suite.
If you want to know which SLA machine to buy, then totally go to AMA, because that's going to be the better place. No, seriously, that's a place where around the bar.
Sure. Yeah.
You'll hear what is the what. People say like, no, this thing doesn't work, or I've returned it, or that kind of thing.
Before we get to our guest, I wanted to introduce our sponsor for this episode, and that is Structure. Structure has been making accessories for the iPad and iPhones for a long time, and they've just released their Structure Sensor 3. This is a great way to get started. I always say that scanning is foundational to a great outcome. Attach it to your iPhone, attach it to your iPad. So if you're looking for a way to get going scanning, I highly suggest that you check out structure.io and look at their Structure Sensor 3.
Awesome, dude. Awesome. So who is our mysterious, long-suffering guest of the day?
Well, I'm excited to have Josh Pelz from Limber Prosthetics. And you may have seen some of the stuff on LinkedIn, but they do, and from the best I can tell, and Josh will be able to explain more of it as we can go in, but they do a single unit prosthesis. So the socket, what we would say is the pylon, and the foot are all connected together and printed as one piece. And what that does is create a super lightweight, waterproof prosthesis. And it does also come with its challenges, which I look forward to hearing about as well. But I love the concept of combining it all together, creating and really focusing on the design side of things, and how do we harness and use advanced and additive manufacturing to create a prosthesis that is a final prosthesis or a definitive prosthesis. So that's about the extent of what I know. So I'm really excited to be learning more as we go.
So welcome to the show, Josh.
Thank you, Joris and Brett. It's great to be here. Brett, you did a great job. I think my job here is done. You've explained the product. Nothing else to say. No, we're thrilled to be doing what we're doing, and I'm sure we'll get into this as we go through this podcast. By 3D printing the entire device, you hit on some of the value. Using lightweighting design methodologies. We're getting 25 to 40% lighter weight than a device that would be typically built with ultralight coats. And so that's just one of those kind of really interesting benefits that came out of the design freedom, the material freedom in additive. And one of the things that is probably the first item commented on by the user when they first put that device on is, wow, this is really lightweight.
That's super cool. We'll get to that. I think we'll circle back to that. Definitely going to circle back to that a bit. But Josh, tell us first off, how did you get involved with prosthetics, orthotics in the first place?
Sure. So I'm going to have to bring this way back, actually, to my childhood. So I grew up in the Pacific Northwest, tons of mountains and forests and trees. But being from Portland, Oregon, there's a lot of rain. And so one of the things I loved doing, and I was lucky enough to do as a kid, was work in my dad's garage and get a real respect and love for craftsmanship, working with your hands, woodworking and metalworking. And I actually think I can really tie all the way back to first loving working with my hands and building a product to really, I think, being able to relate to some of the passion that prosthetists and orthotists have for their trade, for their craft. I grew up in Portland, Oregon, like I said, and going from building go-karts to model airplanes to all that in the garage, found a real love for engineering. That took me to college, several steps later, grad school. And grad school is when I finally, at the University of California, San Diego, actually got connected with a prosthetist, now one of my co-founders and business partners, that really brought me into the field and where I started learning somewhere between 5 and 6 years ago.
That's super cool. And so let's talk a little bit about this integrated device thing, because that's always kind of like, well, it's kind of like when we have very complex devices or assemblies with additive manufacturing, well, always using them instead of a whole bunch of different parts is always what we want to do. It's kind of the holy grail. But you guys managed to do it. So first off, why did you want to do this? And then the next question, I think on the back of that is going to be like, how did you do this? Because that's actually kind of difficult. So first off, why did you want to make this out of like as few parts as possible?
Sure. So I think, when we started this project, we had this concept of an accessible device. And, that was 5 or 6 years ago. We've evolved a lot from then. But I think one was accessibility. How can you make a device that's more broadly accessible both in the US and abroad? But I think there's also a sense in engineering that sort of simplicity can actually be the best way to do something. Actually, as a young engineer, I designed and built a really low tech, but a hand prosthesis, never worn by a patient, but I had the myoelectric activation. I could do a couple different grip poses. And so I think that oftentimes people are really enamored by the next cutting edge robotic hand, the actively powered robotic knee. But we actually really went the opposite direction. And we said, hey, can we actually take the most simple but elegant approach, right, to creating a leg prosthesis? For one, can we take out points of failure, right? Joints are often stress concentrators. 2, can we create a really lightweight device? And then 3, can we create a device that can be sort of scalably manufactured?
Okay, that's cool. And then, and what technology did you choose, or how did you just happen to be working one 3D print technology, end up using in the final device, or how did you choose a different technology?
Sure. So this is actually going back to my undergrad. So when I was doing a degree in materials science, I was doing some undergraduate research, actually in a ceramics lab. Now I've taken a real pivot towards polymer materials, but in that ceramics lab, I was actually given a Lulzbot TAS-4. You both may be familiar with their technology. I think they're now on the TAS-6 Pro or later. But when I was originally given that Lulzbot TAS-4, that was sort of my first, I think that was probably 12 years ago now, to FDM, so filament 3D printing. And actually, I used that same printer, now move forward to a TAS-6, when I printed the very first prosthetic foot. And part of the reason why we chose FDM and why we continue to use FDM was we were able to rapidly iterate. We were able to have a very broad material selection. I think some of the other technologies have started to catch up in terms of breadth of material selection, but FDM still has the most. And we were also able to have the build volume necessary. I believe that multi-jet fusion printers simply cannot, in terms of build volume, print an entire prosthetic leg. With the trim line and the ears going up past the knee, we can be on the order of 650 millimeters in some of our tallest devices. In addition to that, just the idea of deploying the technology, right? It's a lot easier to deploy a printer and a material if you're not worrying about, a liquid vat sloshing resin or a powder bed and some of the complexities of dealing with fine powders.
Okay, that's cool. And then I think the one thing that you really pointed to, which I think makes a lot of sense given the nature of your device, of course, this wide material palette, the fact that you don't have kind of a couple of dozen materials that are very, very similar in case of powder bed fusion, for example, but you have really literally hundreds of different materials. So how did you select the different materials you wanted to work with? Is it really making parts and breaking them, or how did you kind of come up with the final materials you use right today?
Yeah, no, that's a great question. So one of the reasons that I loved doing the degree I did, which was material science, is mechanical testing. I mean, mechanical testing is just plain fun. You create something, often a mechanical test specimen, such as a dog bone, right? Tensile dog bone, and you break it. And then you look at process, structure, property relationships. What material and what process did you make it with? What structures does that material have? Everything from macro structures, so things like fillets that can reduce stress concentrations, down to microstructure. And then you look at properties. How did it perform? What was the strength versus elongation and some of that. So obviously I was able to bring that into Limber, right? Taking that really deep understanding of how do you go through a process, structure, property study, and how do you find the right sort of material and the right process, right? Those go hand in hand for a specific application. So when we started out, actually, our very first device we ever made, we printed out of PLA and then out of PETG. PETG was like that sort of that small improvement in, slightly tougher than PLA, but still fairly brittle when it comes to the material we use today. And I remember we've been lucky enough. So my partner, Herb Barrick, a certified prosthetist and orthotist, practiced for several decades in Southern California. So we always had access to patients and were able to actually work with the end user. But on that first device, we had sort of that first oopsies moment, right? Where we were aware the device may not be strong enough. It was printed from literally a prototyping material, right? And, it's kind of started loading the foot and just like snapped in half, right? Because it was obviously a brittle material, a prototyping material. That was more about understanding, can we print it? Does it fit? Can we get alignment, dialed in? But really that moment was like, geez, we never want to have this happen again, right? I think for the amputee, and I'm not an amputee myself, but I'm sure there'd be a certain level of like, you don't want to feel it re-break, right? If you've had a traumatic, amputation, for example. And so that was sort of an interesting experience for us. Probably more than 4 years ago now, when we sort of used that prototyping material and we're like, well, we'll just test the fit. And it was like, you start loading that thing. And as soon as you get past a certain level, it just kind of brittlely fails. And so that really took us down a multi-year sort of experiment, right? A study into, probably 100 different materials. We weren't doing everything. There are certain materials you can knock out right away because they're just, they're not going to meet maybe the temperature resistance, right? Like, something like PLA, even PETG, right? You could have issues with softening if it's sitting in a hot car. But we basically started going through that process and we tested just a ton of materials. Being at the university, we had ready access to mechanical testing equipment. And so we were able to do really some of the very early on tests where we were taking them up to the ultimate loads, the ultimate P5 load, where, you're just putting it under load with specific setup and boundary conditions. And we would just break things over and over and over and over again. And that sort of allowed us to kind of narrow in on a general property set. We actually use a proprietary material today. You can't create a proprietary material if you don't know what you're going for, if you don't even know what properties you're targeting. And so really to get to where we are today, where we have very tight control over the material we use, required us to take a broad look at what properties actually matter, what properties maybe seem like they could matter but don't, and then start narrowing in on that kind of final material and property set that really works for this kind of unique application of additive in printing that full prosthetic leg.
I think that's an interesting way to look at it too. And I think it's always nice to have another set of eyes kind of come in like what you've done and really take a look at what is important. Where do you feel, when you look at the historical nature of what prosthetists have done with, we can go, wood to laminations to, some of the different materials that we use in the traditional side of things. What have we gotten right and what have we not gotten right when when we're taking a look at traditional manufacturing materials? And then can you tie any of that to the feedback that you're getting now from your proprietary material, the feedback that you're getting from patients?
Sure. Well, that's a really interesting question, Brett. I don't know that I so much can comment on what was done right and wrong in terms of material. I would imagine that there was sort of a time and place and an evolution where, wood probably was the right material at a certain point. That there simply wasn't the way to process, composites, right? At the time wood was used. Actually, funny enough, we have a ancient wooden prosthesis in our lab. And it's like one of those things where, Herb will sometimes joke, Herb started his career carving wood in sockets. And so I think that maybe it's not so much a right versus wrong choice as it is kind of a combination of like, just because you have a material available, you kind of have to have both the material, but you have to have the process, you have to have the right tool set, and those things kind of go hand in hand before you can, safely and responsibly bring, new materials in. I think it's really cool. I mean, my original passion was actually in aerospace. I always wanted to fly. And I think it was very, really amazing that prosthetic and orthotic, the field, kind of embraced those aerospace type materials for sort of the cutting edge foot now, which is that forged carbon fiber material. I think when it comes to material selection for additive, I definitely have more opinions there. And one of the things I think with additive, simply because of the fact that I think there's always more of a chance, regardless of additive technology, that you could have defects or flaws in the build when you're 3D printing. That holds true whether you're using a filament machine, cheap, super expensive, or a multi-jet fusion machine. I think that's when material selection needs to be really tight. I think the knowledge base around wood, you're not going to make a thin wooden member and expect it to not fracture. Same thing with carbon fiber. I think that as those materials were used, there was enough knowledge around them and probably enough of a factor of safety built into those devices that those were the right materials at the time. But I think now with additive manufacturing and being able to so quickly iterate, maybe it's good to now step back, put a little bit more thought into the combination of properties that can make a safe, effective device for a patient.
Yeah. One thing I think is really cool is that you have a co-founder who's a prosthetist, and we've seen it so many times that startups, they say, and it's alluding to what you said before, like we have the mega robot arm, and then they just they blaze in there with their mechanical engineering, robotics expertise or whatever, and they just forget that this whole orthotist product group people can exist, right? And you said one thing is like you have access to patients. And I like the fact that early on you can test things. You can say, hey, does lighter even matter? Maybe these guys I don't want lighter, I don't care. So I like that. But is that could seem, to me, would seem one definite advantage. What are the other advantages of having like a prosthetist as a co-founder?
Sure. Well, just a kind of a funny story. When I first learning about prosthetics, my assumption actually was that you would want to have a prosthetic limb that is the same weight as your sound side. I said,
okay. Yeah.
Otherwise you'd be off balance, right? Now, come to know now it's really about, balance of the weight. You've got a lot less leverage in that amputated side. Your muscles have obviously been cut. That is so true is assumptions, right? Assumptions can really bite you. And obviously nothing's going to replace the benefit of working with both the customer, who's the prosthetist for Limber, as well as the end user, the patient. But I think always being surrounded, and not just surrounded, right? Because it's one thing to have an advisor. I think it's another thing to have someone that's literally running the company with you, really helping to create directionality in the way the business thinks and operates, the DNA of the business. Right. And I think that was critical in us now successfully being in the market. We are selling product, the Unileg, this fully 3D printed below knee prosthesis, into the US market. And we're selling it to the clinician. And I think it would probably be very likely that we would have missed on a lot more had we not had that prosthetist, that clinical mindset kind of built into everything that we've done. So actually, the very first devices that we delivered now almost 3 years ago were in Ensenada, Mexico. And so one of the really cool things is that we've had such a breadth of experiences, both with clinicians, but also patient populations. And I think that was really important also, is understanding how to make a device that can be sort of diverse in terms of the patient populations it can consider. That was actually one of the reasons we decided originally to focus on a below knee prosthesis. Below knee prosthesis to us was a way to, with a single device, help the most people possible get back on their feet. So I think my answer to that, kind of in short, is it's not just having someone that can do clinical design and socket rectification. It's not just having someone that provides access to patient population, but it's actually baking that mindset of patient first, patient outcome first into the DNA of the business. I believe that's one of the reasons why we've been able to get to where we are today.
Yeah, no, I think that's a great point. And also the point of having that person as a co-founder as opposed to your first hire or a contractor or something like that, I think is a really, really big difference as well.
Absolutely.
So talk to us about designing this thing. I mean, first of all, what just really practical, what tools, what software did you use to design Limb and iterate, from CAD to slicing and all the stuff in between?
Sure. So I think you'll both be very familiar with most of these software packages.
Don't say Mesh Mixer, because Joris will lose his mind.
Well, we actually do use mesh mixers for certain mesh mixers.
Everyone uses mesh mixer. This whole industry is running mesh mixer.
So, but actually we didn't start with mesh mixer. We actually started our design process very much kind of away from the mesh side of this. Like the mesh modeling was actually probably a lower lift for us than some of the parametric and topology optimization design that we went through. Because at the end of the day, for us, the socket rectification, that's actually we haven't really taken it upon ourselves to change how sockets are rectified. I mean, the great work that, people like, I think Josh Steer at Radii is doing, there's a lot of people interested, right, in, how do you bring data and some of that into prosthetic socket design. But actually, that's something that we've said, hey, we don't need to reinvent the wheel when it comes to socket design. We're really going to focus on a holistic design approach for the device and sort of design for manufacturing, right? Because the way a traditional pylon and connector and foot are made does not necessarily lend itself to 3D printing of that. And so I would say actually that the big challenges for us was not how do you print a socket, but actually was how do you design and print the pylon ankle foot. And so the software that we used for that, a lot of Fusion 360 and topology, and then Altair Inspire, kind of 3 different packages that sort of we blended together to create our kind of base model, which now we sort of make patient specific through the use of parametric equations, as well as different things. So we're pulling in different patient data, goes into our equations, and that informs everything from foot length, thicknesses of the struts, and how those different things are shaped. But I think one of the coolest things about the way our device is made, and this allows me to nerd out a little bit, is actually the bio-inspiration that was baked into the device. So my co-founder, Luca DeVivo, he's a PhD. He has a PhD in structural engineering. And one of his papers that, you can find this is published in a research journal, is actually on understanding structure property relationships for the cholla cactus based in Southern California. And if you go out into the desert, you might see a cactus that's sort of got some of its flesh, dried or rotted away. And underneath, you'll see this woody skeleton. And that woody skeleton has this really interesting curving geometry. It's ultra lightweight and really strong, really resilient. And so he actually took some of that fundamental design motifs within the cholla cactus, and we used that to inspire the design of our pylon, which is so critical to the weight and the functionality of our device. So that was one of the really cool things, and we did that through topology optimization. And I'll just clarify sort of definitions real quick. I think bioinspiration versus biomimicry, not a lot of people understand the difference. Something like Velcro is actually biomimicry. So Velcro is one of the really classic examples where biomimicry is really taking a geometry or shape or function and trying to copy it. Where bioinspiration, you could create something that looks completely different, but you've taken principles or ideas or inspiration from those natural structures. So if you look at our pylon, it's tangentially similar. It's got holes in it, sort of looks like a lightweighted structure, but it doesn't actually look like a cholla cactus, right? Whereas Velcro, on the other hand, they actually took these natural materials that had these hooks, and they really copied it to create that. That's one of kind of like the classical examples of biomimicry versus bioinspiration, where you can just really take even a single idea or thought or concept, apply it, and kind of iterate off of that.
I think it's good that you bring it up, by the way. I like the idea that the guy was apparently walking with like a sock or something, and a seed burr got caught in the thing. And that's happened to me. And then I think bet it's happened to thousands of people. And that guy ended up like, you know what? I'm going to make a material out of this. So I love Velcro as an example here. And from a point of this is just, I like this generative stuff. It's all very tempting. Implicit modeling is very tempting. Did you think of like developing your own like design system very on, like saying, oh, wow, we're just going to put it all in Grasshopper and just like, infinitely vary it and stuff? Because I do this for certain things, but I mean, did you guys tempted a lot by that? Or were you really trying to make a single design that worked? What was your path to this?
That's a really good question. So being the nerd I am, would love to be generating a unique structure for every single patient. I think there could be a reality where we go there. But today, that would be very difficult to qualify and have a high enough level of confidence that the software is actually taking into account all the intricacies of, this is a material that's additively manufactured in layers with, all sorts of complex relationships with the environment. To expect that a software package could generate 100% of the time a safe and functional device, I'd love it if that were the case. We thought we were going to go that way originally, but what we actually found is that we can generate sort of a base geometry that works really well. And then we can have a much more controlled, parametrized sort of modification of that structure. And so instead of trying to generate a new pylon structure, that new topology optimized sort of 3D curving geometry for every single device, we'll use that same geometry and then we'll make very, very intentional adjustments to thickness and height and width. And that allows us to really qualify a device. Obviously, we are backed by a lot of mechanical testing. We're backed by a quality system. And it would be very difficult to say that, our design space is any generated pylon, right? I mean, I think that's maybe unrealistic, as cool as it would be. And so that's one of the reasons why we basically generated some base model types that we can combine and adjust for that patient. But we're not trying to sort of say, hey, computer, generate me something net new for every single patient, if that makes sense.
I think also, I love the design. I love that it's wide open. It definitely looks lightweight as well. Can you tell us some of the challenges that you've run into, whether it's alignment stuff? Because I saw like this jig that you guys use for doing alignment, or even like some of the printing, FDM printing some of these geometries can definitely introduce probably issues. So yeah, can you just share like some of the challenges that you've had? Like, hey, we've got this really great design, but we're wanting to use this process, even though it's closed, that can be challenging.
Sure. Well, I think actually, you brought up alignment, right? I think that's something that as an engineer, I didn't really, it's like you kind of picture that there's this sort of like perfect alignment. You're like, well, we'll just use software and we'll just use biomechanics and, we'll take a 3D scan of the patient's body and, we'll just get the alignment perfect and it'll be no problem. And then we don't have to realign it. It's like, nope, that is like absolutely not something that's realistic. As the patient's body changes, as their limb matures. I mean, alignment is sort of this living, kind of moving target, right? And I think that's something that I didn't really understand. And even with that co-founder that's lived that, right? It's like from the design side, which Luke and I kind of run more on the CAD side, especially with alignment and inputting that into the design process. It was definitely took sometimes getting it wrong, right? To really understand that you cannot create a 3D printed device, especially if you want to print the whole thing and expect that, it's going to be perfect and it's not going to need to be changed. That was a big challenge because what ended up happening is, we sort of had this concept of this, printing this device in one piece. And there was a point when we said, oh, geez, do we have to throw this out the window? Because we have to adjust it, but how do you adjust it? And that led us down this path of sort of exploration and study to really understand, can you thermoform something? How can you make thermoforming readily, done in a clinical setting, and brought us actually to developing a system, a mechanical system that can provide sort of precise heating of the pylon and enable precise movement to sort of mimic what a pyramid joint or pyramid connector can achieve. But that was one of those areas where, it's like I kept wanting to say perfect alignment. We'll just get the perfect alignment, we'll print it there, and we're done. And it's just not the case, right? That's not how the human body works.
Yeah, I mean, that's interesting that you say that too, because alignment is difficult. As an engineer, what are some other things that you've run into that seems like you should be able to apply math to, but it gets a little frustrating when there's this clinical kind of artistic side as well to the prosthetics?
Sure. Well, I think just, kind of functionality early on when we were doing iteration around our design equations. So we have a set of equations that we use, and we input things like patient weight, the type of activities they're going to do. So, are they doing a lot of skating? Are they doing, mostly hiking, some different, anatomical geometries? And that's baked into equations that then allow us to sort of shape the pylon ankle foot to provide functionality that'll work for that patient. But one of the problems early on was we sort of went into it thinking, again, hey, if you apply engineering, there's sort of an ideal stiffness, there's an ideal flexibility. And that's also not the case, right? Why are there so many prosthetic feet out on the market? Well, it's because not every patient wants the same thing. And so I think a lot of this was understanding that you cannot just engineer your way to a perfect solution when it comes to this field. And I'm sure, other medical fields, you really have to sort of have a way for the customer, in our case, the clinician, and therefore their patient, right? Because their patient's sort of speaking through the clinician to provide maybe some of the intricacies that have to be baked into the design so that they like it, right? Because otherwise it's not going to work for them. And so that's one of the reasons why we love working with prosthetic clinics, is that we've sort of now understand how do we extract the information from the prosthetic clinic? How do we ask them the right questions in our digital workflow so that when we create a device, the patient doesn't put it on and say, this is not what I wanted. And we'll still have that. There's still, always learning to be done, and there's always iteration that can be done. But I definitely think that understanding that it's not just a patient's weight and height is going to give you that ideal stiffness. It's really a lot deeper than that. And you sort of have to talk to the prosthetist, what have they used in the past? What sort of things do they like? And then we can take that and inform our design to really create a personalized device that's going to work for that patient. Because not every patient wants an ultra flexible device. Not every patient wants a really stiff device. And it's some of that understanding that I think we've learned over years of iterating with hundreds of patients that's allowed us to, I think, hit the mark really most of the time in terms of a device the patient steps on and says, this feels pretty good.
So how do people, so let's just say I'm a prosthetist, I'm listening to the Prosthetics and Orthotics podcast. I'm like, go to your website. Oh, that looks pretty neat. How does somebody work with you, or what?
Sure. So basically, to get started with Limber, we can do everything virtually, although we're also happy to send a demo leg. So if a clinic is having a hard time wrapping their head around, obviously we've now started going to the conferences. We will be at AAOP. We'll also be at AOPA later this year. It's always good to get the touchy-feelies on the device. But if a customer wants to start working with us, what we'll do is we have an iPhone app. They will be given a user credentials for that iPhone app. We do a virtual training session, one or more, depending on the comfort level of that individual. And then they can start ordering. Now, the one challenge, right, that we go back to is adjustability. Because of that, when a clinic signs up, we'll actually send a thermoformer, that thermoforming fixture, to their clinic. And so as a part of the sign up, we require each clinic to do a minimum order of 3 legs, and then we'll actually give them the thermoformer for free. So they get that thermoformer, we pay for the shipping, we'll ship it to them. And as long as they continue to order legs, they never have to pay for that unit. That just, we want to reduce the friction, allow people to get into it without a big upfront capital expense, right? So once they start ordering, we've got 3 main workflows. And these have also evolved over time. And I think it's really cool that after years of doing this, we really have 3 main workflows, but those workflows have many sort of forks and branches that you can go down to meet their clinical needs. So we actually don't require, other than entering some data on an iPhone, we don't require any skill in digital design, 3D printing, or digital rectification. We can actually work with a customer that says, I want to use my traditional process. I want to do casting to plaster modification. And I want to try a new, 3D printed device, but I do not want to touch digital. And we have some of those customers. And that works completely fine in our workflow. So they will do their full workflow up to the point they have a rectified plaster positive. They can then scan that in along with providing other information, hit submit on the phone. We take in that data. We may have a question so sometimes we'll dialogue with the customer about the data set we've received. We'll manufacture the device and we'll send it back to them. It's going to have their socket. It's going to have their recommendations in terms of alignment, but we're going to bake in our own sort of secret sauce into alignment and functionality and weight and all of that.
This is super exciting. I think it's super exciting to see you guys develop this. I think it's absolutely wonderful that somebody's trying to do this and trying to make the integral device completely with additive, completely out of as few steps, a few parts as possible. And I think it's absolutely fantastic. So thank you so much for being on the show today, Josh.
Been my pleasure. Like I said, I really have a passion for the industry. It's so cool. I think the first time I stepped into an O&P clinic, I was really blown away by these people are creating things from their hands and getting people back on their feet. And so, it's an easy industry to fall in love with. And it's been our pleasure being able to, add a device, a tool into the tool belt of the prosthetist. And, we're excited to be here and looking forward to scaling. We've got new products on the horizon. So it really is our pleasure to be in this fascinating industry.
Yeah. Brent, I know you enjoy this, and thank you for being here as well today, of course, as always.
Yeah, this was fun. Yeah, thanks, Josh, for kind of sharing your journey. And I always love hearing how people got involved in orthotics and prosthetics when they're not necessarily clinicians. And so, we have a lot of people in our audience that are not clinicians, but they may be students or what have you, and they want to know how they can contribute. So your journey, kind of as the material side of things and the nerd, so to speak, is an important story to share for others, so they know that they can also be involved in changing people's lives, but they don't have to be a clinician to do so. So thanks for that.
All right, awesome stuff. And thank you for listening to another Prosthetics and Orthotics podcast. Have a great day.
And that's a wrap for another episode of the Prosthetics and Orthotics podcast. A special thanks to Josh Pelz for sharing his experience and journey into the prosthetic and orthotic industry and sharing a little bit about Limber Prosthetics. Also, a special thanks to our sponsor, Structure. Go check them out at structure.io. Look for the Structure Sensor 3. If you enjoyed this episode, please leave us a review, give us a thumbs up, share it with your friends. And until next time, we'll see you on the next episode.